I got this from an old textbook. I forget. I think it was like the Larson textbook. But really, it really drives the point home because you have these integrals, and it's in this section called three similar integrals. And you look at it, all the denominators are the same, but how we're going to attack each one is completely different, right? And so, how do we know what to do under what circumstance, right? So the hierarchy is always in this form. Always. Rule, U sub, I'm not going to be like a buffoon and just say everything else, but it really does boil down to that. It's like try a rule, try U substitution, and then try everything else. But really, the everything else boils down to trig substitution, parts, integration by parts, or partial fractions. I mean, but you are really looking for a rule first. All right. How do I know something's going to be a rule? Look for a constant in the numerator. If you see a constant in the numerator, there's a good chance it's going to involve a rule. All right. Now, as it turns out, this happens to be a rule. See, my technique always works. Not necessarily, but it's a good rule of thumb. All right, that happens to be a rule. The second one, so U substitution takes on a lot of different forms. So you define a U so that it helps to cancel out the other part of the integral. All right, so if I were to look at it in this case, I would call U, the more complicated part, U squared plus 1, which would make du equal to 2x dx. All right, but it's even more basic than that, because what I was talking about, all these little notes I wrote on the board, when I was saying, is the top the derivative of the bottom? If that's the case, it's a natural log. But what that is really is U substitution on the fly. If you recognize that the top of a fraction is the derivative or a constant multiple of the derivative of the denominator of a fraction, then you're applying U substitution without writing all the work out. All right, so you're intuitively doing the U substitution. And that's a great thing. If you can pull that off, then you know this stuff. And that's a pretty damn good feeling, I would imagine. So we have du over u, which would be ln of u plus c, which in turn is ln of x squared plus 1 plus c. Here I dropped, you don't have to drop the absolutes, I just dropped them because the sum of squares are always positive.
Couldn't you just taken the 2 out of the integral and at the same answer at the top is 2?
The problem is the x is there. Yeah, that messes it up. Yeah, it's the little things. Now for the third one, we could do partial fractions. We could try a trig substitution. I mean, we got an x squared plus 1. That kind of sort of looks like a partial fraction decomposition technique. Or it could be the trig substitution. It also, like I just mentioned like mere moments ago, that I wasn't going to make you do partial fractions with quadratics on the bottom. So it's like, why are we doing this problem? I brought up this particular example to show you a little nifty trick that helps you avoid issues. All right? So this only works if the powers are the same top and bottom. All right? So I'm going to manufacture a relationship. Story of my life. So I have x squared. I didn't accidentally leave all that space. I need that there for a reason. I just think to myself, I'm like, this would be so easy if only there was an x squared plus 1 on the top. Because then everything would cancel out and it would be like nothing. All right, so I'm just going to do that and hope the teacher doesn't notice. Then cross it all out and just change the problem, right? We've all done that at some point. Well, no, you can't just add 1 to a fraction to part of a fraction, right? It's just not allowed. So I'm going to account for that by also subtracting a 1. Same fraction, right? 1 minus 1 is 0. This is equivalent. But what this allows me to do is a sneaky little move here. It allows me to break up my integral by that minus sign. And so I don't quite get everything I wanted, but I do get some of what I wanted. Still equivalent. X squared plus 1 over x squared plus 1, that's 1. And now I can integrate this very easily because the antiderivative of 1 is x. And what's the antiderivative of 1 over x squared plus 1? Inverse tangent of x. All right, so I could have, like in the homework, I could have tried this with a trig substitution. I would have got the answer. It would have worked out. I mean, in terms of the amount of work, it's not even that bad because we would have a u value of x and an a value of 1. That's not insane. Our triangle would pretty much write itself. You'd have to deal with the x squared on the top, but that would just be tangent squared. So it would clean up, you'd get the answer. But this is so much nicer, all right? But it's the kind of thing like if you don't take a minute and think, like what can I do? And honestly, I didn't even think to do something like this until I was in a moment where I was like, well, I need an answer. I don't know the way I'm supposed to do it. I got to figure something out. Then you start getting creative. And when you start getting creative, sometimes you do stupid things, but then sometimes you catch lightning in a bottle and you're like, whoa, this is awesome. I can do this every time now. You can't do it every time, all right? But you could do it often, all right? Specifically when the powers are the same top and bottom, all right? So then that brings us to the next one where you're like, oh, separating the numerator. Oh, if I could do it for the last one, why can't I do it for this one? This would be great. X over the square root of 1 minus x squared dx plus, well, I'll write it all as one integral. 1 over the square root of 1 minus x squared dx. I don't know why I wrote the dx's in there. I might as well just put the integral in there if I'm going to put the dx's twice. All right, so just separate them up and think. Hierarchy, rule, u sub, everything else. Integration by parts, partial fraction decompositions, and then all that fun trig stuff. All right, so the first thing I would think is, do I have a rule anywhere? Because if I can get a rule for one of these two things, then I'm already halfway done with the problem. All right, is there a rule in here?
Yes.
Yeah, what is it?
Trig sub.
Well, that's a process. Arc, what do we say? Arc something. Arc sine. Arc sine of x. All right, but that's important. Arc something is good enough. All right, that's a good, strong realization. Why? Why is arc something good enough? You know it's a rule, which means you know enough to look at your note card to find that rule, right? You knew enough to know that there was a rule involved, all right? That's like 98% of the battle. Once you recognize there's a rule, you know enough to look at your note card, you put it down on your note card, it's there, you just got to find it, all right? The other part, well, 1 minus x squared, that has a derivative of what? Just the 1 minus x squared. Negative 2x, right? It's so close to being an x. And it's only off by a negative 2. You're only off by a constant multiple. U substitution. U is equal to 1 minus x squared. All right. I went for U sub because that's not a rule. All right. I looked at my formula sheet. I didn't find a rule associated with that. Next step, U substitution. Du equals negative 2x dx. Divide by negative 2. So negative 1/2 du is x dx. So up top, we have the negative 1/2 du. On the bottom, we have the root u, which is really just the same as saying negative 1/2 u to the negative 1/2 du. Which we can integrate. Increase the exponent by 1, comes u to the 1/2. Divide by the new exponent, becomes negative. All right, so I just got to swap out the u for the 1 minus x squared. So therefore, we're looking at negative 1 minus x squared to the 1/2 plus arc sine of x plus c. All right. And you know, I mean, just thinking, you know, in a practical sense, taking a test, I see a problem like this. I get to this step, I have no idea how to do this part, but at least I have this, I already got a good chunk of the credit. You know what I'm saying? So like you start kind of rationalizing it that way. So looking for points. The right way, of course, not the one where you write nonsense and you hope for something, you know. Like you actually give me something to work with. All right? So a disguised log rule. That's interesting. I mean, the title is helpful in that it tells me that I'm going to be using a logarithm in my antiderivative process. But, I mean, I've said this a bunch of times today. When I'm using a log, I need the numerator to be the derivative of the denominator. Well, what's the derivative of the denominator? E to the x. That is not an e to the x. All right? So, let me add an e to the x. That would be great if we could just do that. But we can't, so I'm going to subtract an e to the x. This is like such a cool strategy that I find that people want to do this for everything now. But it doesn't always work. But when it does, it feels great. So 1 plus e to the x over 1 plus e to the x, I'm going to break it up, minus e to the x over 1 plus e to the x dx. So integral of 1 minus e to the x over 1 plus e to the x dx. Antiderivative of 1 is x. And this whole technique, the whole purpose behind this step was to manufacture a numerator that was the derivative of the denominator. All right, so we're good to go. ln of 1 plus e to the x. I don't need the absolutes there either, because 1 is obviously positive, and e is a positive number. If you raise it to any power, it's still going to be positive. But you can never go wrong if you include the absolutes. You'll never lose credit, and you'll never be wrong. That's the more important piece. All right, so, oh, that's it. Hey, units over there.